Hi, welcome back to the Nav Station. I'm Andy Howe. Here at the Nav Station, our goal is to get you confident enough to head out on the ocean, turn off your GPS, and get to where you're going with celestial navigation. In this episode, we're going to look at pre-calculation. We're going to describe 3 different ways to pre-calculate the positions of stars and planets in the sky at particular twilight that you might have to be out on deck to take star or planet sights in. The first method we're going to describe uses volume 1 of HO 249 selected stars. It allows you to pick a basket of stars for a particular twilight, and it's very easy to use, so you can quickly get a list and then go out and shoot them on deck. The second method we're going to look at is using what's known as the Rude or Rudy, R-U-D-E, Starfinder, which is a neat, nice tool for mapping all the navigational stars rather than just 7, as well as planets. Lastly, we're going to look into how to use the planet diagram that's included in the Nautical Almanac. It's got a long description here. We're going to simplify it for you just so you can easily tell if planets will be out in the sky at the time when you want to take sights. So first, 249. What I've done is gone back to the star sight episode where we pre-calculated the times of twilight. And if you need to reference how we got to these numbers, you can just go back and look at that episode again. What I've done is we've picked out the evening twilight, civil twilight, on July 23rd at this dead reckoning position. Sight Reduction Table 249 Volume 1 requires 2 entering arguments. One is an assumed latitude, and we know how to do that already. We're going to take our DR latitude and round it to the nearest whole degree. The other entering argument is the LHA of Aries. And if we recall from all the work we've done before, an LHA is nothing more than taking the GHA of the body, or the point, in this case Aries, and applying your longitude to it. You take the GHA and you subtract west longitude, you take the GHA and you add east longitude. We're in west longitude, so eventually we're going to subtract our assumed longitude. So the first thing to do is to go to the daily page in the almanac for July 23rd. And we're going to be pulling out the GHA of Aries for the hours of twilight, in this case 2200 hours. And when we do that, it's pretty easy. The left-hand page is where the Aries column is located. Find the July 23rd block and go down to the 22nd hour and pick out your GHA of Aries of 271.51.3. Next, we go into the back of the almanac to the increments and corrections page to the 47-minute box. We have no seconds, so we don't have to chase around the seconds. And we're going to pull out the GHA of Aries value there from the Aries column, of course, and that is 1146.9. We add these two together and we end up with the total GHA of Aries, which is 12,893,382. So 283, 38.2 minutes. Next, we are going to apply our assumed longitude, and we're going to be subtracting it because it is west. And we need to make the answer come up with 0 minutes. So we're going to take the degrees and plug them in here, and we're just going to take our minutes and change them to 38.2. So we end up with 0 in the answer. And that is our LHA of Aries, 233. Next, we're going to do our assumed position. So we'll take our latitude of 29 degrees 10 minutes north and round it off to 29 degrees north. And we already have our assumed longitude here. We can write that in so it's all in one place. And there's our assumed position. Now, before we dive into the information we can get out of Volume 1, I just want to show you that Volume 1 is self-contained. There is a table in the back called Table 4, which covers a couple of pages, and this allows you to pull GHA varies information right from this book without having to go back to the almanac. So the only thing you'd really need the almanac for is to correct the site, that is, take your section angle, apply index error, dip, and the altitude correction table for stars or planets. So how do we use this? Well, the first box gives us a value for the first day of the month, and that value is 279.16. So that's July 1. The next box down here allows us to get a GHA value for the 23rd day and the 22nd hour, and that is 3:52:35 minutes. 7:23:22 hours. Obviously, this is a huge number, so let's add it up so we can get rid of the extra 360 degrees, and we end up with 6:31 degrees, 51 minutes. And we'll subtract 360 right off the bat. So we have 51 minutes, 1, 7, and 2. Next, we can go to the second page, which has the minutes and seconds of GHA. And when we do that, the value for 47 minutes is 11:47. Add those together and we get 8. We have 9, we have 3, 8, 2. So it's virtually the same, a couple of tenths difference. So whichever method you like to use, they both end up with the same answer. Now, what you do is you go into the site reduction book. And the site reduction book is set up with south latitudes in the back of the book, north latitudes in the front of the book, and the middle of the book is the equator. And we find the page for 29 degrees north. And that encompasses 2 pages, and it also encompasses 360 degrees of LHA. So we're looking for 233 of LHA. So on that 29 degrees north latitude pages, we find 233, and it'll be over on the right-hand page. That's where the larger numbers are. And we're going to be pulling out 2 numbers, an HC and a ZN. And there's going to be a list of stars we're going to record along with this. So as you read across that 233 LHA line, you see there's 7 stars there. And some of them are all caps, and all the ones that are in all caps are the brightest stars, negative 1.5 magnitude or better. And there's also 3 stars that have a diamond shape next to their name. And those are the 3 best stars to shoot if you really only want to shoot 3 stars, because they're spaced nicely around the boat and they're bright enough to be easily identified. The thing about these stars that are listed here is they span 360 degrees, and they are the best and the brightest and the easiest stars to find in the sky on those bearings around 360 degrees. So it's a good selection of stars that are relatively easy to locate and relatively easy to distinguish in the sky. So the first star we find is Vega on that list, and Vega shows an altitude of 5042 and a ZN of 063. The next star is Altair, which is one of the ones with the diamond next to it, and that's 2611 and a bearing of 094. And we'll stop there. You get the idea. Now, there's two things you can do with this information. One, you can point your sextant sort of in a direction of 063. These are all true, of course. And set your sextant at 50 degrees, roughly 45 minutes, and scan the horizon on that bearing, and you'll see most likely a star that's just above or just below the horizon, fairly bright, just moving along with you as you scan with your mirrors and your sextant. And that's likely Vega. They're not going to give you stars that will be confusing. They're going to give you a star that's going to stand by itself in that sector of the sky. So then you dial in your sextant, bring it down to the horizon cleanly, mark the time, mark the time, and mark the HS for the site, just like you would for any other site, and move on to the next one. In this case, you move a little bit more towards the directly east, and you preset your sextant at 26 degrees 11 minutes, 10 or 11 minutes, and again scan the horizon, and you'll find that Altair is sitting there waiting for you. Take the site, record the time, record your data. So that is the most common way to use this book. The other thing is, if you don't like to preset your sextant, or things are a little dicey out there and you got some clouds, just take a bunch of sites, and you'll note the bearings when you take the site, and then you can match them up later and say, oh, that must have been Vega. That was about 60, 65 degrees pointed in that direction, and it's about 50 degrees and almost 51 degrees of altitude. So presetting works nicely if you're ready to go. Otherwise, you can just start taking sites, and generally you find that you've shot a couple of these anyways. Now, the HS has to be corrected to an HO, just like we did for the sun and the other stars and planets that we described in earlier episodes. When you get to your HO, you're going to compare the HO to whatever the HC is to get your intercept. And you don't have to go back in the site reduction tables to get that information, because you already have it here. This is based, remember, on the time and the position to give us the LHA of Aries. So we've done a lot of that work already. We've got an HC, we got a ZN, so we just need to compare those two to get the intercept and figure out if we start at where the assumed position is, which is HC, are we going to go towards or away to get to where we would have shot the HO? And that's it. You do that for any stars that are listed in this list for this particular entry, and you've got all the information you need. Now, when you go to plot, you have to take into account what's known as Table 5. And Table 5 is in the back of the book. And the reason we have Table 5, and again we'll show this up on the behind me here in a second. Table 5 is a table that corrects for what's known as precession and nutation, which is a fancy way of saying that the Earth isn't doing an even orbit. its axis is a little off, it wobbles a little bit, so it changes the perspective of the stars to us. This book is set up around a central year, in this case what they call Epic 2020. So it's good for 4 years before 2020, and it's good for 4 years after 2020. Everything is 0 in the year 2020, but if you move away from the year 2020, then you have to apply correction for that precession and nutation. And the way you enter it is you find the year, in this case 2021. We've got a box for north latitude and a box for south latitude. We've got latitudes across the top, and we've got LHAs down here. It doesn't seem like a big amount to change things, but you're going to end up with a value that you have to apply to your plot. And in this case, we're going to come up with a value when we do that of 1 nautical mile at 120. That's the information we get out of Table 5. And what that means is that for a site or a fix that you take and then use the information here to calculate your intercept, you need to move that LOP or that fix, if it's exclusively with these stars, 1 nautical mile in a direction of 120 true. And there's several ways to do that. You can move each LOP as you plot it. You can make a fix from the 7 stars you would shoot from this list and move the fix point in that direction, or you can initially move the assumed position in that direction, then everything will be plotted correctly from there. The complication comes in because often you're not just using these 7 stars or some of them. You might be finding other stars that are in better positions or more visible or easier to shoot, and a planet or 2 that might be up that are not listed here. So you have to be careful that the only ones that you move are the ones that come off of this list. The others will be what they are. You might find that by doing these kinds of adjustments, that a fix that didn't look that good is suddenly looking a lot better. And that's always nice to see when you get onto the plotting sheet. So that's volume 1 of 249. Pretty straightforward book. It does give you a list of stars, not all the stars, and it does point out the minimum. If you really just want to take 3 shots, you've got your best 3. But the issue is that the stars that are listed are not always visible at that particular time for a variety of reasons. So it's good to have other ways to find stars and planets to shoot at your particular twilight. And that's what we're going to cover next when we look at the Rudy Starfinder and then the planet diagram in the Nautical Almanac. All right, so let's take a quick look at the Rudy Starfinder, and then we'll go and do a close-up of how to actually use it. So the Rudy Starfinder comes in a nice little pouch, typically, and it comes with a whole bunch of stuff. First thing is the base template, and that has a north side and a south side, labeled right in the middle, which represents the north and south celestial poles. Printed on each side are the 57 navigational stars in their positions relative to each other. Remember, we talked about how stars don't change relative to each other, so we can put them right on there, and then we have some templates that we put over the top that allows us to focus in on the stars that are visible at any one time. So the base template is what we work with mostly, and then we have these grid templates which are for every 10 degrees of latitude. And there's a north latitude side and a south latitude side. It's printed right up in the corner of each template. And what they show is the bearing, here's a 360-degree circle here, and the altitude that you can expect to find a star at. So you pick the template that fits closest to your latitude, and you snap it onto the post in the middle of the base, and you dial in the LHA of Aries, which is listed through 360 degrees on the perimeter. Once you've got that dialed in, you can put a piece of tape over it just to hold it in place. And then every star that is under the grid is what's going to be visible at the time of twilight at this latitude. And starting at the north celestial pole for this particular grid of latitude, these are the bearings through 360 degrees, the Z ends of the star. And then this is the the horizon down here, going up to 90 degrees of altitude. So things down, stars that are under the grid down in this portion are going to be low altitude, and ones up here will be high altitude. So that's the basic use of the Rudy Starfinder. The other use for the Starfinder is as a planet locator. And there is a separate grid here which has, again, 360 degrees around the outside, and that has these slots, has a slot right here. And what you do with this is you calculate something called right ascension, and we'll do that in just a second. And you use that to position the planet template on the grid. And then at the slot, once you've got the right ascension dialed in at the slot, you have north declination towards the pole and south declination in the other direction. And you just look in your Nautical Almanac to find the declination of the planet at that particular time. And then there's a little opening there. You just draw the planet's location right on the grid, and then take the grid off and mark it and label it, and then put your latitude grid on, and you can predict the location of altitude and bearing of the planets that are visible that you plot with this. So a pretty handy little device. Now, the best thing about it, though, is it typically comes with a full set of directions in case you forget how to use it, which happens if you don't do planets with it very often. So what's this right ascension stuff? So first we have, we have templates for every 10 degrees of latitude. We have a north and a south designation, and we're able to pick off the ZN and the altitude of the body. Now, a planet, first of all, with stars, we are familiar with SHA, the sidereal hour angle. And sidereal hour angle is measured to the west from the first point of Aries. Right ascension is measured to the the east from the first point of Aries. So it's very similar, it just goes in the other direction. And of course there's a little formula that goes with it, and it says that right ascension equals the GHA of Aries minus the GHA of the planet. So we'll do an exercise close up, but let's calculate the right ascension of a planet that's going to be visible at that same evening twilight that we just worked on. And that planet happens to be Venus. And the GHA of Aries for that particular time we've already calculated, and that's 283 and 38, we'll just round it off to 38 minutes. Now the GHA of the planet, which we can get from the Nautical Almanac the same way we've always done, in the daily pages and then in the back in the increments and corrections, the GHA for Venus at that particular date, that particular time, is 128. 40, we'll round it off to 48. So if we just really have to worry about big numbers. So let's just subtract 128 from 283 and we get 155 as a right ascension for Venus on that particular time, on that particular day. Again, we're getting a rough position of the planet. As we talked about, planets are pretty visible, pretty obvious which is a planet and which is a star, but it allows you to plot it on the Rudy Starfinder to get an approximate bearing and altitude for that particular planet. So now let's do a close-up look at a template and compare some of the readings we got, from values we got out of volume 1 for this particular twilight, and see how they match up with what we uncover with the Rudy Starfinder template, and also plot the planet on there as well. All right, so here's a close-up view of the Rudy Starfinder setup for the problem we just did. We've got a DR latitude of 29 north, so we picked the 25 north template. That's the closest to our latitude. And we've set up the LHA of Aries here of 233 on the dial. So everything under the grid is visible. This line out here way at the outside is the horizon, and right here is 90 degrees up, straight up overhead. And then these bearing lines radiate out from there, reflecting from 0 around to 360 degrees of bearing, and the altitudes start at the horizon at 0 and go all the way up to 90. So the first star we picked off that list was Vega, and here's Vega on the template, showing a bearing of about 60 degrees. We picked off 63 from volume 1, so that's pretty close, and an altitude of 10, 20, 30, 40, 50. And we picked off an altitude from volume 1 of 50 degrees and 42 minutes. So we've got a match here. We've got a little bit of variability in the latitude, but it's pretty close, and generally speaking, that's going to be fine for our identification purposes. The next star we had was Altair, and here's Altair over here. Another 30 degrees of bearing difference, a little bit south of east. We had 94 from the book, and here we're about 90, about 93, 94. And altitude 10, 20, just under 30 degrees. And the altitude from the book was 26 and change. So that works. And a couple things we can do here. We can validate that we actually shot the star we thought we shot. We can use this to identify stars. Sometimes you've got so little time to take your star sights, you don't want to spend a lot of time trying to set things up exactly according to either the book or what you find here. You just shoot stars as they become visible and record the bearing and worry about what they are later, because you can go to the template here and identify them and say, oh, there was a bright star over in this direction at about that altitude. That must be that star, and so forth. So it's an identification tool as well as a pre-calculation tool. So pretty neat little tool, and let's look at how we attack planets and how we put planets on here. All right, well, here's the planet grid set onto the post, and we've dialed in our right ascension here of 155 that we calculated earlier. So in this opening here is where we're going to make pencil marks to position the planets that we want to shoot onto the grid, and then we will put the 25 north latitude grid on top and get the bearing and altitude calculation. So in this case, this grid, this slot here, allows you to plug in the declination. So here's 0 declination, and north declination is this side, and south declination is this side. So when we look at Venus, the declination from the almanac for that particular day is about 12 degrees north. So we just set this up with the right ascension value, and then we start at 0. We count up about 12 degrees. We make a mark, and that becomes the position for Venus in the sky at that time. And then we would take our grid. So once we've positioned the planet with the planet grid, we take that off, and then we put our latitude grid back on. And right here is where I've positioned Venus, made a dot in a circle, and I could label it Venus if I was going to have multiple planets, but usually there's only one or two, so it's not that difficult to figure out which one's which. And Venus would have a bearing of about 280, 275, and an altitude of about 17 to 18 degrees above the horizon. So by doing this, you get a feel for the number of stars that are visible and any planets that you might calculate as being visible as well. Okay, so that's the Rudy Starfinder, a great little tool. Pick one up. They're very helpful if you're going to be into shooting stars and planets. Now let's take a look at the planet diagram that's in the Nautical Almanac. All right, so here's the planet diagram from the Nautical Almanac. We're going to talk about all the labels I put on it, but there is an explanation of the diagram on the adjoining page in the Almanac. I've never really liked their explanation of how to use it, but the visibility of the planet's description is helpful in determining what constellations they might be in, what times of year they might be up, etc. So you can use those descriptions plus what I hope will be a more helpful description here with this diagram. This originally came from an article in Ocean Navigator by a National Guard pilot, a sailor, and navigator, and I've always liked it, so I try to remember how it's set up and put it in every almanac every year. So first thing you got to understand is that this represents the entire plane of the ecliptic, which is where the sun, the moon, and the planets all travel. So we don't have the moon on here. We could put it on, but that just is unnecessary because the moon is very identifiable, and we know when it's going to be up and when it's not going to be up generally. So I've labeled the top of the diagram east of the sun and the bottom of the diagram west of the sun, and then drawn in two horizontal lines at what is 18 hours and 6 hours, which the times are labeled on the side, and those two lines are labeled 90 east and 90 west, and then the bottom at 0 and 24 and top are labeled 180 west and 180 east. Those are not longitude descriptions, they're descriptions of how many degrees east or west of the sun we're concerned with in the diagram. So if we take a date, like we're looking at July 23rd in our example, so let's just do July 20th because that's labeled there. And that straight line that goes from top to bottom represents a complete day. And at the top and bottom, we are 180 degrees from the sun, which is that shaded band in the middle. And anywhere along that line, on July 20th from top to bottom, where we intersect one of the lines that's labeled as a planet, that will show us approximately when local mean time of meridian passage is, if you look off to the right on the time scale. And obviously, if bodies are too close to the sun, they're not going to be visible. And so we have to remember that ones that are in that shaded area, we just can forget about seeing those at all because they're up with the sun and we can't detect their light. So at any time, only half the diagram is visible in the sky because the sun is rising at sunrise and in the east, that shaded part in the east, and the region that's marked west of the sun is setting in the west. So we're going to see at sunrise the bodies that are just below the shaded area. So in this diagram, we can only see a few days of the year where we've got planets visible at sunrise. Pretty much the first half of the year, and not too much going on the second half of the year, because we can see there's really nothing that is south of that is in that diagram part of the west of the sun part that shows up anytime after June or July. So any planet that's shown on the 12-hour line, which is that line right in the middle, to the bottom of the page is west of the sun and visible only in the morning. And that's why we labeled it on the left, above the horizon at sunrise. So on July 20th, we will possibly see Jupiter and Saturn. And at sunrise, we probably would not detect Mercury, because Mercury is right next to that shaded part that represents the sun. And in the evening, the bodies that are indicated from the 12-hour line to the 24-hour line are going to be visible at sunset. And in that case, on July 20th, we would possibly see Mars and Venus, depending on how bright they were, because they are pretty close to the sun. So that's the basic description of this diagram, and I think just labeling the east of the sun, west of the sun, above the horizon at sunrise, above the horizon at sunset is enough to give you a hint about what's happening, because that differentiates the diagram into two clean halves that we can look at immediately and go, okay, it looks like I have nothing available in the morning or something available in the evening, and you can't pick out the exact position, but at least you know, then you can go in perhaps and use your Rudy Starfinder to pre-calculate the position, or just look for it up in the sky on a particular bearing and find it. So that's the diagram. That's three methods of calculation we've gone through. We're going to do a review after this. Okay, so we've got a lot of information from our three pre-calculation methods. We've got a list of 7 stars from volume 1 of 249. We've potentially got some additional stars from the template with the Rudy Starfinder, and we figured out which planet or planets might be visible at the time of twilight that we're interested in from the Nautical Almanac. So, using that information effectively and efficiently is part of our job as a navigator. We have to be organized when we get out on deck so we can bang off these sites in quick succession before twilight disappears or the boat lurches or a cloud comes up or something happens, because you never have as much time as you think to get these things done. It's best to have an assistant with you, particularly with stars. Sun is very easy. You can take 3 or 4 sun sites by yourself with no problem. Star sites, you really need to have somebody there so you can, once you get the star on the horizon, say mark. They mark the time. They wait for you to give them the sextant reading, and you move on to the next one. So here's what I like to do ahead of time. I like to make up a template, a page that I can make copies of ahead of time, listing the star, the altitude that's pre-calculated, the ZN that's pre-calculated, then the actual star site sextant angle, and the time. You can have a box for date and twilight and whatever else you might want to have on there as well. But that way you can list the 7 stars from volume 1, you can list their pre-calculated altitudes and bearings, and then you're ready to write in the sextant angle and the time. You can also, after looking in the Nautical Almanac, write in the planet or two that may be visible at that twilight. And of course, you don't know the altitude in ZN until you do it from the Rudy Starfinder, and you can write that in too, and then you're ready to go. The other thing you can do with the Rudy Starfinder is select a few other stars from around the boat to fill in the blanks from the list of 7. You may find stars that are easier to identify for you because of their altitude, their brightness, or their familiarity in certain constellations. Record all this information. Then when you go out on deck with this in your notebook or on a clipboard, you can hand it to your assistant with your watch or your timepiece and a little flashlight and a pencil, and they can just be ready to record stuff as you move around the boat taking sights. Another thing I like to do is, especially if I need a cue as to what's going on, make a graphic of the boat, and this heading becomes your course. And I just use 150 magnetic. So you can use this much like you use this form ahead of time, and you could plot where roughly you would expect Altair to be, where another star might be, and around the boat like that. If that's a graphic that works for you, sometimes it's better for me to organize it that way because I tend to be out there and I don't really have time to look at this list and convert the bearing to what it means in terms of where it is on the boat. This is a very fast way to organize yourself out on deck. The other reason I like this is because you can be taking a sight here and you're ready for the next one, and suddenly you see a bright star here and you're not sure what it is because perhaps you didn't write it down in this graphic, it didn't fit any of these on the list, and you can grab that sight and label that as mystery star number 1, and so forth. If you go around the boat and you see another star that you like, mystery star number 2. And you've got the bearing and the altitude, well, the bearing and the section angle and the time recorded. So then you can go back to the Rudy Starfinder and look under the template and see, does a star pop up in this approximate location? Usually you're able to see, well, it's not exactly what I shot and it's not in exactly the right position, but it's pretty close. You can reduce it and see how it works out. Surprisingly, most times that I do this, you find that the star that you pick out of the template is the star that you shot. And if you can't, you figure out what it is, you can back into it if you're really at a loss for stars to use for this particular fix, and do it by process of elimination to find out what star it is. Sometimes that's a lot of work, sometimes it comes easy. But the main thing about this whole process is to be organized. And if you have somebody with you, explain how you're going to shoot the stars and be ready to move around the boat, because you may be shooting off in this direction and somebody says, oh, there's a bright one over here. And you got to shift gears quickly because you don't know, it popped into view, maybe it's going to pop out of view just as quickly. So grab all the information, then go back down below and figure out what you have here and then start doing your sight reduction. The main purpose is to make sure that you get a bunch of stars and planets that will give you good crossing angles on your fix. You don't want all the stars to have very similar bearings. Then the error here is much increased from something like a plot like this. So if you have stars on opposite bearings, you really don't need to use both of them because they're going to end up with parallel lines of position just coming from a different direction. So shoot them both, take the readings, and figure out which one works better with your particular fix. At the end of all this, you should end up with a good fix. I must say that when you take a lot of star sites, they don't always all work out for a variety of reasons. You misidentified the star, you got the time wrong, you did something with your sextant reading that was just wrong, you read a wrong digit somewhere. So the more information you get, the better off you are. Okay, that's the end of this episode. We've got two bodies left to talk about. One, the moon, and one, Polaris and latitude by Polaris, the North Star. So that'll be the next two episodes. Coming up next will be the moon and the moon site. And we look forward to having you back here at the nav station. If you haven't subscribed already, well, you missed a whole lot of good episodes. Go back and look at them and subscribe here, and we'll send you alerts for what's coming up. We do have a few episodes left once we get through the moon and Polaris to cover some other topics. And look forward to seeing you back here at the nav station. Thanks for stopping by.